Okay, so we'll start this workshop. I hope everybody's doing well and with a lot of energy. This is the time of the year that we start feeling a little burnout, and you have to keep on strong because you are in the second half of the semester, second half. So keep it strong, and we'll discuss any questions. I'll stay at the end. I'll help you as much as I can. And we are going to see today the seventh experiment in Labflow, which is acids, bases, buffers, and pH. So what are acids? First questions. At least you have seen in your lectures 3 different definitions. And they all coexist. And each definition looks at a different aspect of acids and bases. Like the definition of Bronsted-Lowry definitions from 1920s. It defines an acid as a substance that can donate protons, and it defines a base as a substance that can accept protons. Protons are hydrogen ions. And acids, just to give you a quick overview, have a sour taste. We find acids in lemons, we find acids in batteries, we find acids in vinegar, and acids sometimes can dissolve some metals. What else can we say about acids? They turn the blue litmus paper, they turn it red. So if you put a drop of acid in a blue litmus paper, it will be red. And how about bases? Bases, we don't find it as much in food because they have a bitter taste. We find them in household products, in drain openers, and they turn the litmus paper blue. So if you put a drop of a base in a litmus paper that is red, it's going to turn blue. Even though we don't find a lot of bases in food because of bitter taste, still some people acquire the bitter taste, like in the chocolate or in coffee, but not that much. So what is today's objective of this experiment? We have a lot of objectives. First thing, what are we going to do? We're going to measure different solutions. So you will have an idea of what is the pH, how acid or how basic are different solutions. That is the first part. Then you will check, you will add a little bit of acid or a little bit of base to a regular solution, to a solution that is not buffered. And you will check how much the pH changed. Like you will see, okay, this solution has an original pH of 7 if it's water, and then you add some acid, how much the pH change. And then you will do the same, you will add the same amount of drops of acid or base to a buffer solution. This is your first exposure to a buffer. Buffer, we are going to go over, this is just a quick overview, are substances that resist the pH change. So you will notice the difference, how little the pH change when you add acids or bases to a buffer. And then it continues towards the end of the experiment. You will do a acid-base titration. How is that titration done? We will go over that, but the objective is to calculate the concentration of acetic acid in vinegar. And then you will you have to report what is the concentration in two different ways: the molarity of the acetic acid and also the percentage. Basically, the percentage of how many grams of acetic acids you have in 100 milliliters of vinegar. They will tell you the brand of the vinegar, and they will say, well, it's about 5%. We use vinegar a lot when you use it in the salad. So as we always do, first, I will share the page of the experiment. We will go over the pages, then we'll do a learning check, and towards the end, we will go over the report to make sure you know how to complete the report. So let's get started. Okay, because for some reason I couldn't upload this as a file, just tell me if you cannot see it. I hope you can see it. I'm sharing as an application in this case. So the first thing that we see when we start reading the write-up of this experiment, in the background, we see here two equations. The first equation is hydrochloric acid that reacts with water to donate a hydronium ion and chloride. So this is the Bronsted-Lowry definition, that an acid donates a proton. It's written here, the proton combined with water. At this point, you already are familiar with that. So when you see the hydronium ion, that is the proton combined with a molecule of water. And then the second equation that you see is a base. The other definition that you have that was before the Bronsted-Lowry definition, the Arrhenius definition, Arrhenius from 1880s, he defines a base as a substance that produces hydroxide ions in aqueous solution. And he also said that an acid is a substance that produces hydronium ions. So this is written that way because the easiest way to recognize a base is to look at the hydroxide. If you have a base that has an OH, like here, sodium hydroxide, then immediately you won't confuse it because you see the OH group and you will say, okay, this is a base. And also the OH group can accept a proton to form water. At this point, that is basic. So if we continue looking at what they are talking in this write-up, then they come that, and they are talking about strong acids. Memorize the list of strong acids. Strong acids, they associate completely in water. That is very important. If you have hydrochloric acid and you put it in water, it dissociates completely. you won't have a molecular hydrochloric acid anymore. And weak acid only dissociate partially. This is what they are talking here. And the reaction is reversible. So we saw reversible reactions in previous workshops. And again here, when we have a weak acid, we use the acid ionization constant, Ka. But that is only for weak acid because we have an equilibrium. We won't have a constant for a strong acid because the reaction proceeds to completion. There is no equilibrium. And here, the first highlighted reaction is showing how the water dissociates in hydronium ion and hydroxide ion. So if you just put water in a container, it's going to be an equilibrium. This is not a reaction that goes to completion. So the water is going to dissociate into hydronium and water. And because there is an equilibrium, the equilibrium constant for this reaction is the product of the concentration of the two ions. Remember, the equilibrium constant is concentration of products, divided by concentration of reactant. When we learn that, we also learn that we don't add in the equilibrium constant, we don't add liquids or acids. Liquids or solids. So that's why the water is not included, the equilibrium constant. So the equilibrium constant for the water is the ion product constant for water, which is Kw. I want to make sure this is basic, but you know these concepts. So if you have water, part of the water, very little is going to dissociate. But if you look at this number here, the constant at 25 degrees, actually I highlighted here because it's written wrong. It says that the Kw is positive. And no, it's not that big. The value, so if you look at that, don't get confused. The correct value is the one that is highlighted, right? Is 1.0 times 10 raised to the minus 14. So when you measure that equilibrium constant for the water at 25 Celsius, you find that this is the value 1.0 times 10 raised to the minus 14. And because if you have just water in the solution, the only ions that you are going to have are the one that comes from this dissociation, which is protons and hydroxide. So both, if you look at the equation, you have one of each. So when you try to, you have the same amount of each. So when you find out the concentration of hydroxide or hydronium ions is going to be 1.0 times 10 to the minus 7. So the concentration of in pure water is 1.0 times 10 raised to the minus 7. And that is pH 7. That is neutral. Any questions so far? I have to go to the other screen because, let me see here. Does the Kw constant contribute to the significant figures? What do you mean in terms of, does the Kw constant contribute to the significant figures? I'm not sure I'm understanding that question. the kWu constant is a constant, and the value is fixed. It's 1.0 times 10 to the minus 14. That is a fixed value. It's never going to change.
If we have something like if we have one figure of 3.14 or something, some random number, I like how I just thought of pi, and that has 3 significant figures, but we only have 2 in this one, does that affect it? Does that make any sense?
Okay, they give us this value like that. So I'm not sure if you are asking when you are calculating the pH from a concentration. Is that what you are asking?
Essentially, yeah. The biggest thing I want to know is if it's considered a constant. So if we have some number in there that's 5 figures or some different number of figures, we don't have to stop at 2 figures because of the because of
Correct.
it's constant.
Correct.
It's 1.0 times 10 to the
Exactly. Exactly. And when you calculate the pH, we will go over from a concentration. I'm sure you know, you look at the number of decimals, right? If the concentration has 3 decimals, then your answer of the pH will have 3 sig figs.
And that's better. Exactly what I was wanting to know. Thank you.
Yes, you're welcome. Awesome. Okay, so I wanted to make sure that you understand that because the concentration of hydronium ions and the concentration of hydroxide ions is the same in water, we know that a neutral pH is 7. It seems basic, but okay, awesome. Okay, so let's continue. Okay, if we look at what else they want to tell us, let me see here in the write-up, what else we have. Basically, they define the pH. That is a measure at the end of the day. We said that the concentration in water of hydronium ions is 1.0 times 10 raised to the minus 7. Because we want to make it simpler, there is a definition of pH that also measures the hydronium ions, which is minus log of the concentration of hydronium ions. So what would be a pH neutral? If the pH is 7, it's going to be neutral, because neutral means that the concentration of hydroxide ions equals the concentration of hydronium ions. That is the definition of neutral. And here they are talking about if the pH is higher than 7, it's going to be basic, and if the pH is lower than 7, it's going to be acidic. That is something that you will have to know it just like secondhand. And why does this come? Because we are going to have a lower pH, lower than 7, when the concentration of hydronium ions is higher than 1.0 times 10 raised to the minus 7, because it's minus log. And then here, they're giving us an example. It says, suppose the concentration of hydronium ion in solution is 1.04 times 10 to the minus 3. So they give you the concentration of hydronium ions. And they ask you to calculate the concentration of hydroxide. can calculate the pH. So what is the first thing that they are showing us to do? We know that it doesn't matter, because it's important to know that the KW will always work. So, and it's a constant. So if the concentration, let's say, in an acidic solution, we have more hydronium ions than hydroxide ions. But that means the constant will still work. So if one increased, the other had to decrease. So the good part is from KW, we can always calculate one or the other. So here, all they are doing is using the KW to calculate the concentration of hydroxide. And the pH, because it's minus log of the concentration of hydronium ions, then we use the concentration of that. This is an easy, very, very simple problems. I'm sure you saw much more difficult problems in lecture. But any questions so far? Okay, so let's then go to buffers. Buffers, I mean, are simple, but you have to understand what are them and how do they work. That is the concept you need to understand in order to solve all the problems that you will see in lectures. Here in the lab, all you have to see is not much. It's about recognizing that buffers are solutions that will resist a change in pH by obviously neutralizing the acid or the base that you add. For example, let's say we add, just to say a number, 0.01 mole of sodium hydroxide, that is a base, to a buffer. I have a buffer that is acetic acid and acetate. And the buffer, I take the pH, and I see that the buffer, the initial pH is 4.74. Then I add the base, I take the pH again, and I see that the buffer is now 4.83. Only changed 0.09 points, obviously up because we added a base. And if we add the same amount of sodium hydroxide to water, the pH changes from, what is the original pH of water? Pure water. 7. Yes, let me check because I have to go to another screen. Okay, nobody said anything. Yes, 7. Awesome. Correct. Thank you. So it changes from 7 to 12. 5 points. So that is the important, that's what the buffers do. Basically resist the change in pH. And that is not something very, it is very important. Many solutions need to have a constant or almost constant pH. For example, you have read it, our blood has to have a pH between 730 and 740, kind of like that, because the proteins only function in that, around that pH. So the body uses buffers, and one important buffer that the body has is this buffer that is written here on the left, that is a mixture of carbonic acid and carbonate. I had to write it here. And how do the basically buffers usually consist of a weak acid, which is this carbonic acid, and a conjugate base, which is the salt. Or it can also be a weak base and a conjugate acid. So how do the buffers work? Let's say that we have the buffer in the blood. Let's say we add a base. The body brings a base. And here, if we add a base, the part of the acid is going to react with the base. If you add an acid, the base is going to react. And that's the way they function. So here, it forms more base. You are adding a base, and it forms the acid is making more conjugate base. And then what happens? You have these two, the carbonic acid and the bicarbonate. So what happens? We saw what happens when we add a base. Now, here is reverse. See that the arrow is written in reverse. So look first to the right side. These are the reactants. If you are adding an acid, H3O plus, instead of reacting the carbonic acid, is going to react the bicarbonate part of the buffer to produce more acid and water. So this is how the buffers work. And we make a simple buffer just mixing acetic acid and salt, for example, sodium acetate in water. And these two pairs, the only difference is one proton. This one lost carbonic acid, lost one proton to produce the conjugate base. So this is just what they are giving us in the background, but we will study how buffered solutions and unbuffered solutions are affected by the addition of an acid and a base. So when we get there, you will know how it works. As long as the amount of hydroxide, let's say here, that we add is less than the amount of this carbonic acid in solution, the buffer neutralizes all the sodium hydroxide, and we have a pH change that is very, very small. Any questions on how the buffer works? Okay, so then we'll go to the next part, which is the acid-base titration. The last part of the experiment is to do a neutralization reaction. What is a neutralization reaction? We know it from Chem 1, but just refresh. It's a reaction where an acid reacts with a base to form salt and water. Here we have, when you hear neutralization reaction, okay, an acid, hydrochloric acid, reacts with sodium hydroxide to produce a salt, sodium chloride, and water. And what is a titration? You have seen, I hope, you will have a video to watch. Watch the video in Labflow about the setup of a titration. And I think you have two videos to have an idea how a pH meter works. So you are going to understand more. So don't miss those. I I forgot to say that when the neutralization reaction is complete, here you have a salt and water. What that does mean? That the concentration of hydroxide ions is the same as the concentration of proton ions. That is called neutralization. And when we go, we said, what is titration? Titration is just a method to determine the concentration of an unknown, which is our analyte. Our analyte is the unknown. So we slowly add, let me see if I have a drawing here. I add, let me see, here. Okay. So you are going to have this setup, right? You will have a burette. Here, instead of, you are going to use a beaker instead of this Erlenmeyer flask, but you're going to have a beaker, and you are going to put in the beaker your unknown, which is your analyte. In our case, is going to be vinegar, because you are trying to see how much acetic acid is in the vinegar. And here in the burette, you will have your titrant. Your titrant, basically, we slowly add our titrant. That is a solution. In our case, is going to be sodium hydroxide, a base. We add slowly our titrant to the analyte, and when we do that, we check the pH. We can check it with a pH meter or with an indicator. In our case, we are going to use an indicator. We are going to use phenolphthalein. And then at the equivalent point, we are going to slowly add until the indicator changes the color. So that is our end point of the titration. So with the correct, if we use, let's say, phenolphthalein, the end point of the titration, as soon as we see that it turns pink, not that much intense, just a very little pink, clear pink, the end point is very close to the equivalence point. Don't confuse both. The end point is when the color change. And what is the equivalence point? What happens is, in theory, the equivalence point is where the number of moles of the base is stoichiometrically equal to the number of moles of the acid. So we have this reaction right here. Acetic acid that is in the beaker. And then we are adding sodium hydroxide from the red, that's our titrant, to slowly neutralize. And the equivalence point is when, in this reaction, is 1:1. 1 mole of sodium hydroxide reacts with 1 mole of acetic acid. But we cannot, the way to be close to that equivalence point is to use an indicator that will be very close to the equivalent point. Basically, and why does it change the color? That's another thing. Because the phenolphthalein, the acid form of phenolphthalein, has no color. So you will add in the beaker here your vinegar and a few drops of phenolphthalein. And it's going to have no color, because that is the color of phenolphthalein when it's acid. And then you start adding base. And then the color of the phenolphthalein in basic solution is pink. And that's how you know we are at the end point. We are close to the equivalence points. And one drop of the base near the end point is usually enough to change the color of the indicator. Any questions so far? Let me check here. Would the solution be neutral at the equivalence point? Yes. Perfect. Exactly. That is an important concept.
So the equivalence point is when we achieve neutrality, but the endpoint is whenever we've. I don't understand the endpoint exactly.
The difference. Okay. So the equivalence point is in theory, the exact point we try to see as close as we can. But we define the equivalent point when the number of, here you have a reaction, like is acetic acid reacts with one mole with 1 mole. So the moment that is exactly the number of moles of the base is exactly equal to the number of mole of the acid. In this case, we don't even have to say stoichiometrical. It's stoichiometrical, but it's 1-to-1. The titration is complete, which means there is no more acid. And then we stop. So this is the theory. It's like the theoretical is what you call is the equivalence point is that point. But now we want to see that point. When we use an indicator, we cannot say that is exactly. We want an indicator is as close as possible, but we call it the end point. Basically, is what we see, is the point when we stopped adding our titrant because the color changed. So is basically what we can do. Does it make sense?
A bit. I just wanted to make sure that I understood. The equivalence point is when we achieve balance, and the endpoint is whenever we can really see that balance. It's not the most ideal. The equivalence point is the most ideal, but the endpoint is whenever we actually observe it. Did I understand that?
Yes, exactly. The equivalent point is if you are calculating, you can calculate the equivalent point. If you say in theory 1 mole of this, you know the equivalent point when it's going to be. But the other one is when you observe it. In theory, with a good with the correct indicator, the end point of the titration is very, very close to the equivalent point, because we are trying to use an indicator to know where is the equivalent point, because all our calculations, but it is as you said, the end point is when we see the coloring change. It should be, in theory, very close with the equivalence point. Does it make sense?
Almost completely. The only thing that I'm wondering is, does it have to achieve a certain pH for the equivalence point?
Okay, that will depend. You will see when you study, probably in the next one, in the next experiment, probably you will have a better idea, or you saw that in the lecture. Basically, in this case, we have a weak acid titrated with a strong base. So the endpoint, the pH, will be a little basic. But if you are titrating, that will depend on the pH curve. You know those curves that have an S shape?
Yes.
From lecture? Okay, so if you are titrating a strong acid with a strong base, then the equivalence point will be exactly at 7. Yes, but if you start the initial pH, let's say of the acid, because you are titrating a strong acid, will be maybe 1, and then the equivalence point will be at 7. But the difference of the curve, the pH curve, when you are titrating a weak acid, is that the initial pH is a little higher. It's not maybe 1, it's maybe 2 point something, and then the equivalence point is going to be at maybe 8, at a little. It's not going to be exactly at 7 because you have a weak acid.
So if we're playing with the strong acids and the strong bases, then we can get the neutrals 7, but otherwise we can get it balanced, and the equivalence point is whenever we get it stoichiometrically balanced.
Exactly. It's not about the pH. It's about if you are titrating. Exactly. Yes.
Thank you so much.
You're welcome. Okay. So then let's go back here. And what else we need to add about titration? So when we get to do the report, all the concepts are clear. Otherwise, this is an experiment that you really need to understand the concepts. Otherwise, you are doing it blind and it doesn't make any sense. Okay, so here is the molarity of acetic acid. They basically, they are explaining how you are going to calculate the molarity. This is the easiest part of the, I believe so, of the experiment, because when you stop the titration, because you saw the color change at the end point, you will read in your burette the volume of sodium hydroxide that you used. They will give you the initial volume in the burette and the final volume. So the difference will be how much volume of sodium hydroxide you used. And then you will be given the molarity of sodium hydroxide, and then the volume of the vinegar that you titrated. So it's very simple. They are showing you here. First, how do we calculate the moles? Volume times molarity. The volume in liters times molarity is going to give us the number of moles of sodium hydroxide. And because we saw in this equation that is 1:1, the number of moles of sodium hydroxide equals the number of moles of acetic acid. So here, the moles of acetic acid equals the moles of sodium hydroxide, because the ratio here is 1:1. They find this from the equation. And then, once you calculate the moles of acetic acid, obviously molarity is number of moles per volume in liters. So they will tell you how much volume you add to the beaker, and that's how you are going to calculate the molarity. And then the last part of the report is to calculate the mass volume percent of acetic acid. And that is also very simple for you. What is the formula? The formula is given here. Is the grams of acetic acid divided by the volume of acetic acid times 100. And the mass, if we know the moles, we only have to multiply the molar mass. So that is simple. This quick overview, any questions on this quick overview? Would there be a buffer if the pH change is negative? Depends. Yes, you can. The buffer resists a change. in pH. It's going to be depending on what, it could be a buffer, even though the change is negative. Of course, all you have to look is how much the pH changed. If buffers will make the pH to change very little, and if the pH, like the example that I gave you, when pH changes like 5 points, like when you add sodium hydroxide to water, it's going to change a lot. But if you add the same amount to a buffer, then it's going to be less. Does it make sense? Okay, so let's then go to do some learning checks. Agree with you. Exactly. Thank you, Alonso. Exactly. The buffer is going to make the pH change. What is the change specifically? That is not, depends on which buffer we have, depends on what are you adding. If you are adding a base, it's going to go up. If you are getting an acid, it's going to go down, and depends on how much base or acid you have, and also what is the capacity of the buffer. What are the concentrations of the buffer? What kind of buffer you have? And how close are to the pH when the buffer is more effective. So each buffer is different. Let's look at, I have another text. Okay, thank you. Okay, awesome. Let's look, you are going to tell me these, determine if the following substances are acids or bases. Let's look at A. Let's remember, these are easy. Remember the definitions. We said, what do we say about an acid? What do we say? How the Bronsted-Lowry said that an acid has a proton. Exactly, thank you. Yes, it's a proton donor. Exactly. So when we have to say if it's an acid or if it's a base, it's very easy. Usually it's at the beginning, right? So what is A? It's an acid or it's a base? It's an acid, because it can donate a proton. How it's going to dissociate?
I believe we're looking at a hydrogen ion and chlorate.
Exactly, thank you. And you put this acid in water, it's going to give you this proton. And because it can donate a proton, we say it's an acid. This is really okay. So we are going to say acid. How about B? Acid, thank you. Exactly. It's going to dissociate. Somebody said a base. Base is C, or we are still in B. So if we have ammonia, ammonia can donate, actually ammonium can form ammonia plus a proton. It can donate a proton. Then it's an acid. But if I tell you, I got it confused. Yes, actually, yes. And it's easy to confuse. So we have to look at this. This is an acid. And this is the conjugate base. Conjugate base. This is confusing. That's why I took the time actually to do a little bit more than what you need for the experiment to make sense. I hope it helps. So this should be easy. We look at and donate. Oh, you're very welcome. Thank you. So it's easy this to confuse, but what you are going to do is look at this, and they say it's an acid. Can ammonium, because actually I said ammonia, can ammonium donate a proton? Yes, it can form ammonia and a proton. But if I ask you, how about, is this an acid or is this a base? You will say a base because it won't donate that proton. Can only, exactly, can only join, can only form ammonium accepting a proton. So it is confusing. So this is the acid because it donates a proton. And this is the base because accept the proton. Any questions there? Okay, so let's go to the next one. This one, sodium hydroxide. Base, yes. Those are, when you see the OH, yes, you're going to say it's a base. And now let's look at the next one. What is the next one? It's an acid? Yes, exactly. Thank you. Kyuhan, this is a base. This is harder to recognize because we don't see here the OH. Because if we see an OH, we say base, but we don't see it. So how are we going to know? We can even use the definition of Lewis that a base donates electrons, but because, yes, exactly, it's the conjugate base of a weak acid, that's a weak base. Yes, exactly. So what you can do is look at this and say, can this donate a proton? No, because it doesn't have one. Can it accept a proton? Yes, it can, because it forms hydrofluoric acid. So then we are going to say that it's a base. Even though another way is, when you do the Lewis structure, you know fluoride is in group 7. I don't want to confuse you more. So it has 7 electrons, but because it has an extra electron, fluoride, it has a pair of electrons that can be donated. That is the last definition probably seen in lecture, but you don't have to do that. You can look in an easier way here and say, okay, the fluoride cannot donate a proton, but can accept one. Yes, it's the conjugate base of a weak acid. Very good. And how about the last one? Yes, awesome. Yes, it's called amphoteric. Yes, exactly. Very good. That's why I put it. What happens when it acts? It can be an acid or can be a base, like the water, amphoteric. So what happens? It forms carbonic acid. Exactly, thank you. And what happens? Yes, exactly. And what happens if it loses? If it donates a proton? When it donates a proton, exactly, thank you, exactly. So in the first case, this one, it's an acid or it's a base? Bicarbonate, in the first chemical reaction, is acting as an acid or acting as a base? Base. Very good. Because it's accepting a proton. Very good. And how about in the second one? It's acting as an acid because it's donating a proton. Very good. I guess in this one you are good. And now, the second question here. What is a neutralization reaction? I know you saw it many times, but just to make sure. Reaction between strong acid and strong base to form neutral salt and water. Yes, it's a reaction exactly, an acid and a base. Yes, it doesn't have to be strong acid and strong base. As long as it's an acid and a base. So a neutralization reaction basically is a reaction between, in this case, yes, we have, let's say, a reaction between, here we have a strong acid. We have an acid that reacts with a base to form the salt plus water. So that is a neutralization. If you look at this, I don't know if you remember from Chem 1, it's kind of a double replacement reaction because this reacts with hydroxide to form the water. And the chloride reacts with the sodium to form the salt. So if you look at this is a double replacement reaction. So the water is the combination of the hydrogen here and the hydroxide. And the salt is a combination of the sodium and chloride. So this is all it is for a neutralization reaction, a reaction with an acid and a base that forms salt and water. Just to make sure. Okay. Then what else do they ask here? Let me see. Okay. It says, what is the setup of a titration? I'm not sure if you had a chance to do it, but watch the videos so you know what you are talking about. I saw you that drawing that you are going to have a beaker with the acid here. Here you're going to have the acetic acid. Plus the phenolphthalein. And then you will have burette, which is your titrant. This is not a nice drawing, but this is kind of, doesn't look really good, but I'm hoping. Here, you're going to have your sodium hydroxide, your titrant. So basically, just for you to see what is the setup of this titration. So you will add slowly here, drop by drop. You will know the volume of the acetic acid that you have here, and you will add the sodium hydroxide until the end point, which is the point that the phenolphthalein. Okay. Actually, the first time, question, I wrote it with one. I actually seen it both ways, but I decided I used to write it like a second with a double T. But I cannot guarantee because I've seen it both ways. So I believe the second is better. Burette with double T. Yes. So we have the burette here, and we fill it with our titrant, and we add until the end point. This is the setup. What is the second question? What solution goes inside the burette? That I wrote it like that. I used to write it without two T's, without the E, but now it changed. Okay, so who answered that? They spell it red in the videos. Okay. Base. Yes, thank you, Kyuhan. Exactly, which base? You are going to read the procedure and you are going to see. Yes, thank you. Awesome. What solution goes inside the burette? Okay, here. What is the name of the solution? Okay, what is the name of the solution inside? In general, how do we call it? The solution that we know the concentration, because we know the concentration of sodium hydroxide. We are recording, we are adding slowly until the end point, and then we record the volume. We call this solution inside the burette, we call titrant. And which one we analyze in our experiment? The acid is our analyte. It is the substance in the beaker that we are trying to find out the concentration. That is our analyte. And the titrant, we just said it, is the solution that we add slowly to record the endpoint volume. And the last one, what is the color of the indicator at the endpoint? Yes, thank you. So the phenolphthalein, actually the previous question says what indicator we use. We use phenolphthalein. And phenolphthalein has no color in acidic solutions and pink color in basic solution. Once all the acid reacted with the base, the end point, which is the end point, if we add more base, then the color will change. The excess of hydroxide ion will make the solution pink. That's how we know the end point. And then the last question, it says, okay, what aspects of the titration are important to obtain a good result? So these are things that you will see videos, but so look at the video so you will see what is a good technique. First of all, you have to make sure that you do not pass the end point. It has to be a clear ping. Otherwise, you keep on adding, and when you record your volume is going to be wrong. It's going to be higher than what it is. As soon as you see the ping, you stop. and then you record the correct volume. So that is one of the errors that we see frequently in the lab. And then how we read. Be familiar on how to read the burette. The meniscus always has to be at eye level, and you have to check for bubbles in the burette before you start. So the volume is recorded correctly. And then do you remember how to read the scale in the burette? In the burette, the volume markings increase going down. And then how do you always, that you remember, you always have to report the readings with one estimated digit. You learned it became 1, but just to refresh it, only one estimated digit past the smallest marking. And then always look at the bottom of the meniscus. So all those details are important in the technique in order to obtain a good result. Any questions here? So then we'll move into the report and see what do you have to complete. I hope that after all you heard from me, it should be very, very simple to do the report, because I gave you more than what well, no, you need all those concepts. I gave you what you need. Okay, so when you are going to open the first, you're going to do the quiz, watch all the videos. Then when the time of the report comes, in the lab, if you were in the lab, you will have to do all this. But because you are not there, you will be given all this data. For example, vinegar. You will test the pH with, you can use pH paper or let me see. Okay, so pH paper will give you the color and then the pH, estimated pH, and then using your pH meter. It's obviously more exact using the pH meter. And then you will let this, take a look and see, oh, vinegar is acid, ammonia is basic. So all this in red is information that you are going to have. Everything is given. All this is given. Even the amount of the vinegar is White House, and the volume of the vinegar you will need to calculate the molarity, it says 5 ml. And then all in red is given. The first thing you have to complete here, they only ask you if you have to complete if it's acidic, basic, or neutral. That is easy peasy for you, because you're going to look at this. 2.3. Is it acidic or is it basic? Anybody can tell me that. Yes, acidic. Exactly. Thank you. Awesome. Perfect. Exactly. So if it's less than 7, acidic. If it's higher than 7, basic. And then if it's 7, it's neutral. So here you have Anton and yes, Ala?
Yes. So we're looking for the pH meter, or we're gonna go use for the paper?
I will look at the pH meter.
Okay.
Yes, it's more exact. The
Okay,
other
thank you.
one can give you you're welcome. Would antacid be neutral or basic? That will be neutral, because look at the values of using the pH meter. That is more exact. So here you have a 7, and then it's going to be neutral. So this is the first thing that you have to do, and it's very easy. Then the second part that you have to do, I see some text messages. Okay, I already answered. Okay, so then here, pH change, it says, okay, you have water, right? Initial pH is 5.7, 5.1. After 5 drops of hydrochloric acid, it's 2.7. After 10 drops, it's 2.3. So they will ask you for the pH change and if it's a buffer, yes or no. So the pH, here they're saying when recording the pH change, if the final pH is lower than the origin pH, the change will be a negative number. So you will have different numbers than me, but use after 10 drops, use this one. So basically for the pH change, you will do final 2.3 minus 5.1. So I get minus 2.8. Is that right? Yes. So for me, I do this one, final, minus this one. And then I got minus 2.8 in my case. And then, is this a buffer? Yes or no? No, exactly. How can it be a buffer if the pH changed 2.8 points? And then you will see that this one, higher pH, if you do that, you are going to see, and they are actually telling you. So this is really no-brainer because they are telling you. So this change, if you do the same as before with my numbers, is minus 0.6. It's less than 1 point. So yes, it is a buffer. And here I got minus 0.4. And yes, it is a buffer. So let's look at one thing. Here, you are adding an acid. Which one of these two buffers change the pH less? The one that says low pH buffer, because it's more effective when they call low pH buffer, it's more effective when you add acids. So here, the pH change, they're both buffers, but the pH change is a little lower because this is a buffer that is for acids. This is just an extra point. They don't ask you about that. Then when we look at the next part, same thing. Same thing. You do the same thing and you will say if it's a buffer or if it's not a buffer. And then what else you have to do? The acid-base titration. So how are you going to calculate here the volume here? How do we calculate that? You have the initial volume, basically when you fill the burette with sodium hydroxide, they ask you not to try to do it exactly at 0 because they wanted to, if there is an error, to compensate with the two readings. So they are giving you an initial volume and a final volume. And how do you calculate the volume of the sodium hydroxide used? It's basically the difference, right? 43.01. Exactly. What number do you get? What should I write here? Yes, thank you. Exactly. So here you will have a number, 42 times 59. And then you do the same here and the same here. So you have 3 trials. You did the experiment 3 times. And then, how do you do the average volume? That's easy. Yes, exactly. Very good. So the average, this plus this plus this, exactly. Okay, so that should be easy. How, and here in the first one, they say in milliliters. And then you divide by 1,000, is you will need it in liters. So that is easy. How do we calculate the moles of sodium hydroxide used? That's easy also. The number of moles of sodium hydroxide is going to be what? The concentration of the molarity of the sodium hydroxide times the volume in liters, but we are going to use the average, right? So we are going to use, let me see, here, average volume, this one. We are going to use the average volume in liters. So we know that the molarity, and the molarity of sodium hydroxide is given somewhere, right? It's this one, 0.0979. So all that information we have times the average volume, we are going to obtain the number of moles of sodium hydroxide. And then what is the number of moles of acetic acid? This one. Yes, volume times molarity is the number of moles. That is what we did, same as base. Yes, exactly. So this is what we did for sodium hydroxide. Because the reaction is 1:1, the ratio is equals the number of moles of acetic acid. So the numbers that we are going to have here and here are the same. Any questions so far? Okay, we know that the reaction, when we saw the equation, is 1 mole of sodium hydroxide reacts with 1 mole of acetic acid. And then they ask here for the molarity. What is molarity? Number of moles divided by the volume in liters, right? Number of moles, we have it here. And the volume in liters is what? We come up here, and it says volume of vinegar used is 5 mLs. But we have to, exactly, thank you, Kevin. Exactly, the volume that we are going to write is 0.005 liter. Perfect, okay. So that's how we calculate the molarity. And then the last part is we are asking of the mass of the acetic acid. How do we calculate the mass? You have the number of moles. So you multiply by the molar mass and you get the mass, right? So the mass, okay, of the acetic acid is going to be the number of moles of acetic acid times the molar mass, right? Okay, let's say it's grams per mole, kind of. Do it, I did it probably approximate. So that's how you are going to calculate the mass. And once you have the mass, you just use formula. The formula, the regular formula that says the percentage, obviously is going to be its mass volume, is going to be the mass of the acetic acid times 100 divided by the volume of acetic acid in milliliters. So we are going to write 5. 5 milliliters. And it should be around 5%, which is the percentage of acetic acid in the vinegar that we use in the salad. Any questions so far? Is the image of, I mean, I would do it. I would look if that is a question for your instructor, but I would just do it and upload it, or look if it has point in your report. You can check with instructor, but I would just upload it. It doesn't hurt. And I think I'm going to conclude the recording here, and I will stay because I know Kevin wanted to talk about something, about not sure what. And also, if you have additional questions of anything, I will be here. So thank you, everybody.